Hello, welcome back to centripetal acceleration and uniform circular motion. There's a lot of times where the centripetal force will naturally be the right amount to travel around in a circle. For example, if you swung a ball around on a string, that tension is gonna match the necessary centripetal force. If you swing it faster, the tension in the string is gonna go up until you swing it so fast that the string can't break it, can't handle it, and it breaks. In which case, that object is no longer going to be undergoing uniform circular motion. It's going to be traveling in a straight line path until another force acts upon it. Um, so if something has just the right amount of centripetal force, it'll travel around in uniform circular motion, basically in a circular path at a constant speed. So we're going to swing around an object in a vertical circle, which means basically it's going to be traveling up and down as it travels in a circle. So at the top of its path, it'll be the highest, and then when it swings, it'll be at the lowest bottom of its path when it's the lowest. Um, and we're going to swing it around at a constant speed somehow. We're going to cleverly swing it around. So when it's at the top, the centripetal force needs to point to the center of the circle, which is going to be down. Okay? And when it's at the bottom, the centripetal force needs to point up. Okay? So there's two forces that are going on here. There's the force of tension and the force of gravity. Those two forces provide the centripetal force. The net force between the force of gravity and the force of tension is the centripetal force. Okay, it's the net force is the centripetal force. When it's at the bottom, gravity is pointing away from the way the centripetal acceleration is pointed. So when it's at the bottom, centripetal force needs to point up. Gravity is pointing down, which means that the force of tension has to make up the difference. So the tension is higher at the bottom. Okay. When it's at the top of the swing, gravity points in the direction of the centripetal force. We want the centripetal force at the top is pointed down. Okay. Gravity points down, and so the force of tension only has to make up the difference between gravity and the required centripetal force. So a little bit. So at the tension, it's not very at the top, it's not very tight. Okay, so what we're going to do is figure out, we're going to swing a ball of mass m cleverly on a swing so that it moves in uniform circular motion on a string length r, and we're going to find the tension in the top, in the string at the top and the bottom. So let's look at it at the bottom first. So we're going to say, so if we look at our force diagram, gravity is going to be down, tension is going to be up. Okay, and then there's my dot. We're going to say up is positive because that's the direction that centripetal force has to point. Okay, so in order for this to be traveling around in uniform circular motion, there has got to be a net force in the upwards direction, and that's going to be the difference between tension and gravity. So we're going to say that the sum of the forces in the y direction equal mass times centripetal acceleration. There's no forces in the x direction, and then the y direction, F net equals Fc. F sub c. So, all right, mass times centripetal acceleration equals Ft minus Fg. Okay, so Ft up minus Fg down. Okay, substituting in and solving for Ft. So substituting in mg for Fg and solving for Ft, we get the force of tension equals mass times centripetal acceleration plus mass times gravity. So basically, the tension has got to equal gravity plus the required centripetal force. So, and then we can pull out m and you get a sub c plus g. So at the bottom, or at the top of the path, the centripetal force has got to point down. So that's the direction we're going to choose to be our positive, is going to be down. And there's no forces in the x, and the forces in the y direction have to balance out so that that's equal to the centripetal force. So sum of the forces y equal m a sub c. Now if we look at our force diagram, we've got the force of tension is down and the force of gravity is also down. So our net force is equal to Ft plus Fg because they're adding together. Substituting in for mg and solving for ft, we get ft equals ma sub c minus mg. So we get centripetal force equals centripetal acceleration minus the acceleration due to gravity. So that is how you do at the top and the bottom of the swing of a circle. Now, if you were to swing this slower and slower, eventually this a sub c is going to be less than gravity. And the slowest you can swing it around and have tension in the string is when the centripetal acceleration is equal to gravity, when it's at the top. When the centripetal acceleration is equal to 9.8, equal to g, then the tension in the string is 0. If we swing it around any slower, the centripetal acceleration decreases. We're going to end up with negative tension. So it's actually the string is going to go slack, which is it's not going to be traveling in uniform circular motion anymore. So that's kind of what we said here. So basically, the slowest I can swing, I usually have a cup of water on a string, and I swing it around in a vertical circle. And you can see as I swing it slower and slower, the string gets less and less tension. And eventually, if I swing it slow enough, the string will go slack and the water will slosh out. I usually don't let it do that, but okay. So we got Mr. Freeze has an inverted loop with an effective radius of 20 meters at the top. What is the minimum speed required to make the loop without restraints? So basically what we're saying is, what's the slowest we can spin the ball without the string going slack? Okay. So at the minimum speed, there's no other forces. There's only one force. That's the force of gravity. If we go faster than the minimum speed, then there's a normal force between the rails and the coaster car and my body that push me to the center of the circle. If I go slower, that goes slack, and I'm not in my seat. I'm kind of free floating. So basically, what we're going to say is that the force in the y direction equals mass times centripetal acceleration. Okay. The mass times acceleration equals my one force, my net force, which is just the force of gravity. And so what we get is that a sub c equals g. Okay. Substituting in for vt squared over r for a sub c, we get that the tangential velocity, that the minimum tangential velocity I can go is equal to the square root of rg. Notice mass cancels out again. And so the minimum speed I can make it is 14 meters per second. If I go faster than that, my seat is going to push my butt to the center of the circle. If I go slower than that, okay, I could fall out of my seat. So, and if you've ever been to Six Flags and ridden one of those rides that kind of spins you in a vertical circle, this tension at the top and the bottom should make some sense. When you're at the bottom of the circle, you feel really, really heavy. That's where the tension in the string is the greatest. Okay, in the quote unquote string, or the normal force in this case, the normal force is the greatest. And at the top, you feel the lightest, where the tension is the least, where you're subtracting. And that's where you could fall out of your seat if you're moving too slow. Okay. I don't know if you've ever wondered why turns, like on the interstate, exit ramps and entrance ramps, the curves are typically banked, which means that they're not flat roads. I think, do racetracks do this? I'm not sure. It seems like some of them do. And the reason that they're banked is that when you're on a flat turn, okay, and you're going around the turn, the normal force points up, the force of gravity points down, and the only force that's available to give you any centripetal force is the force of friction. This is like the penny on the Lazy Susan. So the force of friction is providing you all the centripetal force. These aren't providing any of it. Now, if the roads are icy, the force of friction is limited. So you can only take the turn, at a certain speed, whatever your friction allows. If they bank the roads, then part of this normal force, a component of this normal force, will be in the direction of the centripetal force, which would be to the right, in this case, to the right. So it'll have a component in the direction of the centripetal force. So there's a certain speed that you can take a turn at that you don't require friction whatsoever, and we could figure that out, but we're skipping that. Okay. So taking a minor break away from pure uniform circular motion, what does centripetal acceleration do? What does that cause an object to do? Well, it's always perpendicular to the tangential velocity, so it always causes it to turn, never speed up or slow down. What would tangential acceleration do? Well, that would be in the direction either with or against the motion of the object, so that would cause an object to speed up or slow down. If an object is in uniform circular motion, there's no tangential velocity. I don't know what it's doing. So if an object speeds up or slows down, so if we were to spin an object in a vertical circle, and this might look a little bit more like it would do. It would speed up as it went down, and it would slow down as it went up. So there's still centripetal acceleration. There would also be some tangential acceleration from gravity. We're not going to do much with this, so don't let this really mess with your mind. But that tangential acceleration is what's causing it to speed up on the right part and slow down on the left part. So why is there no tangential velocity on the bottom and top? Because gravity and the tension are both parallel to the centripetal acceleration. Okay, so that's it for the centripetal force part of this. We're going to talk a little bit about gravity next, and so you can do all the centripetal force problems. So go and have a go with those.